Alright, welcome back. I'm going to continue with Convergence of Infinite Series Part 2. I did Convergence of Series and stopped before I could get to ratio and root test and the rest of them. So I'm going to take a look at some more test for infinite series where I will denote my sequences as a sub n and series as summation of a sub n. It goes from 1 to infinity unless I stated otherwise. So I'm going to start with the first theorem for today. Theorem, the famous ratio test. Like if you have taken calculus 2, you definitely know what ratio test is. And for ratio test, suppose you have, you're given a sequence an, and that's positive for any, let's say I pick capital N, and again, as I said, is positive, and my sequence is denoted as a sub n. For all little n, which is the sub n, that's greater or equals the capital N that I picked, and suppose I find the limit of a sub n plus 1 over a sub n, and I got a limit, and I'm going to call it L. So these things are going to happen. Number one, if L, which is the limit that I just found, using the ratio a n plus 1 over a sub n, if it is less than 1, remember a sub n is positive, if it is less than 1, then the series an converges. That's it. So since you know that a sub n is positive, your L is going to be between 0 to 1, and 1 is not included. So that's one thing you have to pay attention. What happens if the limit L is greater than 1, which is like 1.1, and so this is not including 1 again. So we can just come up with the result. Diverges. L could even be infinity. Of course it diverges. And now what happens in this case? When L is equals 1, unfortunately this test will be inconclusive. So we'll have to come and decide of what other test to use in this case. Alright, the next theorem I'm going to take a look here is another famous root test. So when I'm teaching or when I'm tutoring, I come across a lot of questions. How do I know what's happening? So again, suppose we have sequence a sub n, and remember this is sequence in is always real. So I'm going to write all shortcuts, so you want to listen what I say. It's a non-negative, so an is greater or equal to 0. So non-negative, and then suppose you have capital N, that's a marker, if you know what's a marker in real analysis. So when all these things happen, and suppose I can find a limit as n approaches infinity for that sequence, and I find the nth root of that sequence. So since I've already told you that an is non-negative, I do not have to say absolute value in the square root, but it's no harm for you to do that. And let's say I ended up getting a limit, and I'm going to call it L again. So these three cases can happen. So only one can happen. So very similar to ratio test, if L is less than 1, the series itself converges, and again L has to be between 0 inclusive, 1 not including. If L is greater than 1, then your guess, of course it would be diverges. Again, L can be infinity, so it will be diverges. And finally, if L is equals 1, then we're going to say this test is inconclusive. In some of your math books or real analysis books, they do not include the last part. But if you have studied calculus, that's something we stress on, so you have to go forward and think of other things. What am I going to do? Alright, the next famous test, all the tests we're going to do here is of course famous, so I'm going to keep calling them famous. We're going to take a look at, this is theorem again. All these things needs to be proved, but right now I'm just going over theorems and definitions. we're going to take a look at alternating. So alternating means, of course, alternating series. And here we're going to take a look at the test and what the theorem says about this. So again, suppose you have a sequence and it's positive. So we can say that the summation of -1 to the power of n, include the negative, and the summation of -1 to the power of n plus 1. These are called, by definition, these are both alternating series. We will say that if we have this, these two conditions must be met. So A, if I can find a limit as n approaches infinity for a sub n. So you're going to keep your -1 to the power of n and -1 to the power of n plus 1 times a sub n. I missed a sub n here. You want to make sure you have a sub n. That's the sequence. If the sequence itself is 0, you know 0 times anything is 0 anyway. And these two things must happen. And if the next thing, if you find that a sub n plus 1, the next term is less than a n for all n, then we're going to say the series converges. It cannot be just one of it, it has to be both for alternating series. Okay, when we're doing examples in the future, you will see some things will look alike, but it's not alternating series. So what you have to remember here, since you know the theorem says this, you want to remember what is the definition of alternating series. It's pretty much very straightforward. All you have to do is look for series. And if you have sequences, and let's call a sub n, where an is non-negative, then the summation of -1 to the n and -1 to the n plus 1, it doesn't matter if you use a sub k, means it will be -1 to the power of k. A sub n, -1 to the power of sub n. These two are called alternating series. So remember, in every theorem that you have or anything you want to try to prove, you want to use definitions, because definitions are something you can always use in any theorems that you're going to prove, or any question that's asking for proof. Alright, the next theorem we're going to take a look at here is absolute convergence. Okay, in order for you to do absolute convergence, you want to know the definition of absolute convergence, right? So that we can use that definition. So let's take a look at absolute convergence. And again, we're talking about series here. So I'll include both absolute convergence and also conditional. How do I know this is conditionally convergence? So let's talk about absolute first. So suppose we have infinite series a sub n that goes, so n goes from 1 to infinity. Even though I don't write it, that's what it means here. So we will say that a sub n is absolutely, ABS, I'm abbreviating it, absolutely convergent if, so remember this is a definition, right? So you just need to know what it means. So we'll say that the series is absolutely convergent if the absolute value of the series, so summation of absolute value n, that's also infinite series, converges. So in other words, if the absolute value converges, the series itself is convergent. Then the next one is if a sub n, so, oh no, not if, sorry, a sub n is conditionally, so you have a condition where it's convergent. For the first part, you just say, okay, the series convergent. You did whatever test and it ended up that it's convergent. If the absolute value of the sequence is convergent. So here this is conditionally convergent if it has more statement than above, if the summation of an is the series converges, But if you notice, we're not talking about the absolute value of the series, but just the series converges, but the absolute value, which is different from part A above or part 1 above, diverges. So it has a condition. It only converges conditionally, and that's the meaning of here. So how would the theorem look like for absolute convergence? So the theorem for absolute convergence would look like this. So absolute convergence. So if the series, the summation of absolute value of A sub n, again n goes from 1 to infinity, converges, we know by definition that only happens when A sub n converges. So we will say then A sub n, series of A sub n, converges. So that's basically what absolute convergence is all about, and that is all for today. And the next lecture or next video I'm going to make is going to include more theorems, more definitions for beginners or for those who want to recall, and finally you are going to be able to apply them in examples, which I will absolutely add. Keep watching. Thank you.